Hello and welcome. In this video, we're going to talk about the 4 elementary series that we have been discovering in our previous videos, and we're going to talk about how you can use those series in different ways. So let's go ahead and jump right in. So the first thing that we're going to do is just define or identify these elementary power series that have already been defined. So we have seen or derived all 4 of these power series in previous videos. So this is not the first time that we're seeing them, but it is the first time that we're putting all 4 of them together and saying we need to know these power series. We need to recognize if something looks like a manipulation of one of these power series. And by knowing these power series, we can identify a power series or a manipulation of the function sine or cosine or e or natural log and make our lives a lot easier. So what we're going to focus on in this lesson is how to use these power series that we already know to write a variation for a different power series. So how do we find the power series for sine of x squared if we know that this power series up here is the power series for sine of x? Well, we could just take x squared and substitute it in for all of our x's. How do we find another manipulation of cosine or e or all kinds of different functions? How do we maybe use integration to help us with some natural log problems? Then we're going to talk about if you're given a series that looks a lot like one of these, can you identify what the original function is? And then lastly, we're going to use a series to find an exact value of one of these 4 functions at a particular value or at a particular number. So the key thing here is you need to know and recognize these. So write them on an index card or on a Post-it, bring them with you, quiz yourself, make sure you know these 4 series. But what we're going to do in this video is focus on how to use them. So let's actually just jump into some examples where we're going to use these power series to manipulate and find a new power series. So I'm actually going to leave those series up top, just make them a little smaller. And here we're going to find the power series for sine of x squared. So this is sort of like what we did in 8.3 part 2, where we used what we knew was a power series to find another one. So we know what sine of x is. Sine of x is up top. If we're looking for sine of x squared, what we need to do is take x squared and plug that in for each of our x's here. And that's going to give us a new power series. So if I write this out, so I'm using the sine power series here, and I'm changing all of my x's to be x squareds. So the first term in the series of sine of x is just x, so that's going to become x squared instead of x. The second term is minus x to the third, so now this is going to be x squared to the third over 3 factorial, plus x squared to the 5th over 5 factorial, plus, nope, not plus, minus x squared to the 7th over 7 factorial plus dot, dot, dot. So it does ask us to find the first 4 terms and the general term. So manipulating the general term, we have negative 1 to the n times x squared to the 2n plus 1 over 2n plus 1 factorial plus dot, dot, dot. And then let's go ahead and just make this look a little nicer. This is x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial plus dot, dot, dot. And then we could simplify our general term as well. This is going to be x to the 4n plus 2 over 2n plus 1 factorial plus dot, dot, dot. So what we just did was we took the power series that we knew was true for sine, and we used that to write a power series for sine of x squared. Let's go ahead and do something really similar, but let's do it with cosine. All right, so now we're going to look at cosine of the square root of x, and actually I'm going to change that to be x to the power of 1/2, cosine of x to the power of 1/2. So go ahead and use direct substitution, change all of your x's to be x to the power of 1/2 in the series for cosine. Write the first 4 terms in the general term. So the first term is still going to be 1 minus x to the 1/2 squared over 2 factorial plus x to the 1/2 to the 4th over 4 factorial minus x to the 1/2 to the 6th over 6 factorial plus ... Let's get our general rule in here. -1 to the n times x to the 1/2 to the 2n all over 2n factorial plus ... And then again, let's clean this up. This is 1 minus x over 2 factorial plus x squared over 4 factorial minus x to the 3rd over 6 factorial plus ... plus -1 to the n times x to the n over 2n quantity factorial plus ... So something I want you to notice is that normally when we see cosine, we're looking at even powered terms, x squared, x to the 4th, x to the 6th. But by manipulating it, by taking the cosine of the square root of x, this is a cosine series of x to the 1/2 that has actually every power, right? To the power of 0, to the power of 1, squared, cubed. So the numerator here doesn't really look like what we're familiar with as cosine anymore, and that sometimes makes it hard to recognize what's going on. The one thing that hasn't changed on this variation is the denominator. The denominators still look like cosine, 2 factorial, 4 factorial, 6 factorial. So when we're looking at a given power series and trying to figure out what that function is, we're looking for those key things that help us identify what type of function we're looking at. So even factorials help us identify that we're talking about cosine. Okay, I'm going to put 2 more up on the screen for you to work through, and I'm going to encourage you to try and do them on your own, but let me get them on the screen for you first. Okay, so here we have x e to the x and 1 over x. So I'm going to encourage you to see if you can figure out, number 3 is not so tricky, number 4 is a little harder. See if you can figure out how to use one of these 4 power series to come up with the power series indicated here. So hopefully you had some time to work through number 3. All we have to do on number 3 is just multiply this entire series by x. So I'm not sure why there's 2 equal signs here, but this is going to be x times the series for e, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... I'll get the general term in here, down here. So this is going to be x plus x squared plus x to the 3rd over 2 factorial plus x to the 4th over 3 factorial plus ... plus x to the n plus 1 over n factorial plus ... So that's how we can get x e to the x. Just take the series for e to the x and multiply it by x. I'm going to create more room for us to work through 1 over x, but I'm going to give you a hint if you haven't tried that one yet. We know that 1 over x is the derivative of natural log, so could you use what you know about this series and what you know about the derivative of natural log to come up with a power series for 1 over x? Okay, so we know that 1 over x is the derivative of natural log of x, which means that it is the derivative of this entire series up here. So x minus 1 plus, not plus, minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 to the 4th over 4 plus ... I'm running out of space. So let's go ahead and simplify this. So this is going to be equal to, well, the derivative of x minus 1 is just 1. Minus, I'm going to drop the power down, so 2 times x minus 1 over 2. Well, those 2's are going to divide out. Plus 3 times x minus 1 squared over 3 minus 4 times x minus 1 to the 3rd over 4. Plus, I am going to put the general term in now, -1 to the n times n times x to the n minus 1 over n plus dot, dot, dot. And then we can simplify this. Those are going to divide out. So we're going to have 1 minus x minus 1 plus x minus 1 quantity squared minus x minus 1 to the third plus dot, dot, dot. And you can see that that general term is going to become x minus 1 to the n minus 1 plus dot, 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 because our denominators are dividing out everywhere. The other thing I want to point out about this problem, and we were told in the directions here to use an elementary series, but this could also be represented as a geometric series, 1 over 1 minus, if I wanted to make that 0, 1 minus x, and then you could use what you know about a geometric power series to write that one out. So I just wanted to point that out. You could represent that function, 1 over x, as a geometric power series if the directions were worded differently. You're actually going to get the exact same result as you got here, except here we have x minus 1 instead of negative 1, or instead of 1 minus x. But the concept here, you're still going to get exactly what you're looking for. So we're going to do one more like this together where we are representing something as a power series, and then we're going to look at the other end where we are identifying things given a series. So let's make room for our last example of this type. So here we're going to look at the integral from 0 to t of natural log of x plus 1. So this is the same thing. We actually know this series natural log of x plus 1 is the same as the series for natural log up here, except it's going to be centered at 0. And we came up with that in one of our earlier videos. So I'm just going to rewrite what this is with the series in place of natural log of x plus 1. So here is the power series for natural log of x plus 1. And you can add that to your list up here if you didn't have that written down. We did come up with that in a different section. So now we're just going to integrate with respect to x and then evaluate that at the bounds from 0 to t. So if I integrate this, I'm just going to get x squared over 2 minus x to the third over 2 times 3 plus x to the fourth over 3 times 4. I'm just going to put 12 minus x to the fifth over 4 times 5 is 20 plus dot, 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 negative 1 to the n, x to the n plus 1 over n times n plus 1 plus dot, dot, dot. And we're evaluating this from 0 to t, so I don't need a plus c anywhere here. Notice that if we plug 0 in, every single one of these terms is going to be 0. So this integral is just going to be equal to what we get if we substitute t in. So t squared over 2 minus t to the third over 6 plus t to the fourth over 12 minus t to the fifth over 20 plus dot, dot, dot plus negative 1 to the n times t to the n plus 1 over n times n plus 1 plus dot, dot, dot. So that's going to give us our antiderivative here, our integral from 0 to t of natural log of x plus 1 dx. And that is coming from the power series. So instead of integrating natural log of x plus 1, we can actually evaluate it using the series. Now we're going to move into recognizing some elementary series, and I'm going to try and help you identify the things that I look for when I'm recognizing those. I'm going to keep those series on the top up here so that you can see them, but let me go ahead and get some problems down here for us. Okay, here we have 6 and 7. We are given two series, and we are being asked to write each as a function using an elementary series. So we are being told that each of these is an elementary series. We need to figure out which series it is. So I'm going to write this as f of x equals, and we are looking for what function is this. Well, the first thing that I'm looking at is the denominators. When I look at the denominators, the very first thing that I notice is that there are no factorials. X, 2x, 3x, 4x. So both sine and cosine and e, all three of those involve factorials. So if this is an elementary series, it doesn't have anything to do with those factorials because there are no factorials there. That leaves me with natural log. So I'm going to look at natural log. I see 1, 2, 3, 4, but now I'm seeing x, 2x, 3x, 4x. So it seems like no matter what I'm doing, I have an x that's being multiplied into the denominator of the normal function for natural log of x. And in order to get natural log of x, I need to have natural log of x here. Now I want to check and make sure that there's nothing else that's different. So do I just have the natural log of x series with just an x multiplied into the denominator? I'm going to double check. The only difference here is the over x. Yep. Minus the only difference here is over 2x. Yep. So it does look like this is the function to represent our series. So looking for the key things that help you identify which of the four it is that you're talking about, and then figuring out what manipulation has got you here. So when I look at 7, I notice factorials. So I'm not talking about natural log here. I'm talking about one of these threes. Now I want to look more carefully at these factorials. What I notice is I have 2, 3, 4. So I don't just have odd factorials like I would with sine, and I don't just have even factorials like I would with cosine. So that's leading me to think that I have some sort of manipulation of e to the x. Now I want to notice, so I'm just going to put e, something going on with e here. Now I want to notice what's different. Nothing is different in the denominators. But I do notice that the signs are alternating. So in regular e to the x, it's always positive, but I have a negative, a positive, a negative, a positive. So that's going to mean that this exponent needs to be negative. Instead of just e to the x, it's going to be e to the negative something. That's how I'm going to make the sign alternate. What I also notice is different. My first terms are the same, but this x becomes negative x squared. So let's see what happens if I just put negative x squared in. Does that get me what I need for all of my terms here? Well, if I put negative x squared in here, I would get minus x squared. Good. If I put it in here, negative x squared to the second power would become positive x to the fourth over 2 factorial. That works. If I put negative x squared in here, I'd get negative x to the 6th power over 3 factorial. And we do, in fact, have our function. So again, you're looking for what's going on with the factorials. Are there factorials? Are they odd or even? Then you're looking at how that could be a manipulation of whichever function it seems to be going with. Okay, let's look at exact values. So in these last couple examples, we're not going to have any x's at all. We're going to be looking at a power series that represents the exact value of a function. So the first thing I want to encourage you to do is don't figure out exactly what we are talking about, but just see if you can figure out which elementary series goes with each of these functions. So go ahead and pause the video and see if you can identify which elementary series goes with each of these functions. Okay, I'm hoping that you figured out that 8 has got to have something to do with natural log. And 9 looks a lot like the sine function, and I'm going to tell you why in just a minute. But the reason I noticed that 8 looks like natural log is because, again, there's no factorials in the denominator. And this looks exactly like the natural log function. The only difference in the natural log series up here and this is that where I had an x, I have an e. Well, what that means is this series is equal to natural log of e, which we know is just 1. So this series is representing natural log of e, which means this series is 1. It converges to be 1. That is the value of the infinite sum of this series. For number 9, I noticed that I have odd factorials down here. That's what made me think sine. The only difference is that I'm seeing here is that I don't have this first term where I would have something, just the x, right? X minus x to the third over 3 factorial. So I'm wondering where that first term went. Other than that, it looks like the only thing that's different is that in the spot where there was an x, so in each of these spots, there is a 2. So the two things that I noticed, I'm talking in some way about sine of 2, except because there's a term missing here, I'm going to have to subtract out what that term would be. Well, if x was 2, then I'm going to have to subtract a 2 out because that 2 that would normally show up in the sine series isn't there. So this is representing sine of 2 minus 2. That is the exact value of that series, or that is the infinite sum. So the key ideas in this section, we need to be able to recognize the 4 key power series. We need to be able to use them to create a new power series that's a manipulation of one of them. We need to be able to use them to identify when a series is a manipulation of one of them. And we need to be able to identify when we have the exact value of an elementary series and what that exact value is. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.